Welcome, everyone, to Your Attention, Please, Optimizing Metrics for Humans, a talk by me, John Feminella. I work for a wonderful company called Pivotal, which you've probably heard of at some point during your time here at Spring One. And I have the privilege and the pleasure of working with a lot of different types of clients, but I mostly work with large banks, financial institutions, and insurance. And this talk grew out of a sense that I got of how those companies and those organizations were building their monitoring systems and looking at these complex distributed systems that they had that they wanted to make sure were healthy. I saw some patterns emerge from the way that these different groups were doing their monitoring. And so that's the genesis of this talk. When we want to understand the health of a system, whether it's distributed or not, there are lots of things we could measure. There are lots of things we could choose from that will help us understand how well or how poorly that system is doing. So, sort of the traditional things we might think about off the top of our heads are things like disk I/O or compute or memory. And because of recent improvements in computing power and data storage costs and other important variables over the last several years, it's really practical now, if you wanted to generate huge amounts of metrics with extremely high granularity and then send all those metrics somewhere to some data store and store them forever so that you can look at them at some point later on. That's possible to do with that level of fidelity for almost any system for not a very high cost. So just to throw some numbers out there, how cheap might it be to do that? Well, let's say we have a system that generates 100 different metric streams per instance. So each one of these is like something that's emitting data points like a CPU usage as a fraction of the overall CPU compute, memory usage as expressed as a number of gigabytes, et cetera. So each one of those is a stream of data points. And let's suppose that there are 100 such streams in this particular system that we'd like to monitor. And let's say that we sample that stream one time per second. So we take one sample per second per stream. And let's say that there are 24 bytes in each sample. So that's enough to record a 64-bit timestamp, some number of interest that's also 64 bits, and then another 64 bits of metadata. So that's 2,400 bytes per second per instance of this system. So if you had 100 instances of this system, let's say it's maybe a Kubernetes cluster. It has 100 pods in it, and these are the metrics you're measuring from each of the pods. That would be 240,000 bytes per second. And if you do that over a year, it's about 7.5 terabytes per year. Now, if you wanted to store this and pay for the storage somewhere, let's say in S3, that would only cost you about $175 a year in US East 1 or a comparable region. So that's not very expensive for a whole year's worth of running this system. You can get you only have to pay $175, and you would get a down to 1 second granularity measurement of the 100 metrics across all of the time that system is running. So it seems like this is kind of a no-brainer for enterprises. You should store everything in case there's ever a problem so that you can diagnose that problem later on and you have as many metrics at your disposal as possible. So later when you discover some kind of issue, you can say, well, what was it that caused that issue? And you'll have a lot of metrics at your disposal. So for a lot of organizations, that seems like an attractive proposition. If you can measure it and it's cheap to measure it, why wouldn't you measure everything you possibly could to help you understand how a system is functioning? And in this talk, I want to argue that just because we could measure something doesn't mean we should measure something. Like that fun quote from Jurassic Park, just because your scientists were so quick to think about whether they could, but they didn't stop to think about whether they should. And then we got dinosaurs running amok and eating that lawyer guy. And in fact, I think that in a distributed system, most of what you could measure is almost completely useless for determining the health or understanding the health of that system. And furthermore, I would also like to argue that even among what you do measure, you shouldn't show most of what you measure to people at a first pass if those people are responsible for understanding or maintaining the health of that system. So if this seems like a crazy idea or you're intrigued by this, greetings, welcome to the talk. So the first aspect here is that ultimately humans are responsible for running, at least for now anyway, running large systems and organizations. So if some system goes down, maybe it's maybe you have something like Bosch, or you have some monitoring agent that will restart the system or parts of the system for you. But the blame for the system, the ultimate responsibility for the health of the system, at some point in the chain rests with the human, whether that's the CEO of a company that maintains medical records. Ultimately he or she is going to be accountable to the shareholders for maintaining that system. So even if there's a lot of automated pieces in the way, ultimately we're still talking about humans maintaining some system. And humans, as it may or may not surprise you to learn, are subject to all kinds of cognitive biases and are very prone to making certain categories of mistakes. And one of the more interesting properties of the way that we try to understand complexity is that we have a really strong inherent disposition to simple, elegant solutions. And we perceive these to be sort of inherently good. You may be familiar with this equation called Euler's identity. Mathematicians have called this one of the most beautiful equations ever because it unifies 5 of math's fundamental constants into sort of this neat, consumable package. And this predisposition to these simple, readily digestible answers is really good has been really good for humans over the length of our existence. If you have to think too hard when you need to make a quick decision, like should I run away from this scary-looking animal, you might be dead. So it's beneficial that we often want these simple, clear answers to things. But that predisposition also comes with a bit of a price. Because even when we're not in distress, or even when we don't need to make a quick decision, we have still tried to comprehend complex asynchronous distributed systems by searching for simple, straightforward ways to understand them. So lightning storms, for example, are terrifying if you don't know how they work, if you're not familiar with the way, with what electrons are and how charge builds up over a large area of ground cover. Then that can be really scary when a lightning bolt comes down from the sky and blasts you to pieces. Because if we're a human from a few millennia ago, we may not understand how storms work. So if we want to stay alive, we need to understand that. But if we need a quick and simple way to understand how storms work, and we don't really understand anything about weather, we're probably going to have to invent some explanation for why storms are the way they are. And that's why every culture, pretty much going back for the last 5,000 to 10,000 years, has every major culture has some kind of storm deity or some kind of wind deity that explains why storms happen or why weather is the way it is. So, and this isn't just the case for one deity. Every kind of complex distributed system we interact with in nature, there's probably a deity for that in a culture that's been around for long enough. So every time there's a pattern of humans who want to understand a complex system, we look for simple explanations to that complex system. And as our knowledge about the world increased, we stopped needing tools like deities and religions to explain how everything works. So if you understand how gravity works, you don't need a gravity deity. You can get by with just that. So this approach really took off in the Enlightenment era, the middle of the last millennium, and people began to value aspects like rationality and deduction. The core strength of an idea is how much it told you about the world around you and how much it enabled you to predict what will happen next. And one manifestation of this was a new way of thinking about distributed systems. Now, the type of distributed system you'd encounter as an average Middle Ages citizen would be something like nature. So that would probably be the distributed system you'd be most familiar with, is the ecology of the world around you, whether that was hills or meadows or forests and so on. So nature, of course, is an extremely, extremely, extremely complicated distributed system, much more complicated than any of us could ever hope to represent or replicate with something as crude as computers. But that didn't stop humanity from trying to do it anyway. It wasn't long before people started thinking, how can I bring together the ideas of science and nature to make life better for my fellow humans? In other words, how can I optimize for the effectiveness of this distributed system and control it in some way? How can I figure out what matters most to me about this distributed system and optimize for the variables that I would like to optimize for. And it turns out that in the late 17th and 18th centuries, a few countries got really, really interested in this idea. And it was common at the time for governments to own large tracts of forests. And they would lease these forests to commoners who wanted to chop down wood or build their house or have a homestead or whatever. It's sort of like a strategic natural reserve, but for wood. And the state was very interested in maximizing the output of these forests, of maximizing the amount of timber that could be milled from the forests. And timber is valuable for construction, houses, shipbuilding, all kinds of other reasons. So the state was very interested in having these forests be productive. And two countries in particular were very interested, Saxony and Prussia, which are two parts of what would now be considered modern-day Germany. They had a lot of state-owned forests. And they said, well, you know, the way we're going to optimize this forest is to try to understand what are the variables that go into optimizing the amount of wood that a tree produces? How do we figure that out? So they wondered if it was possible to optimize for timber yield. So first what they did was they figured out what trees had the optimal yield for timber, and then they cut down all the trees that weren't those trees and planted long, straight rows of the trees that had the best output. And then they said, okay, we're going to have those long, straight rows, and we're going to parcel them up in different ways and try different experiments. So in some areas of land, the rows will be closer together, and we'll trim the trees a little bit less often, and so on. So they were running lots and lots and lots of simultaneous experiments to try and figure out what the exact values were of like soil density and irrigation and so on in order to figure out how do we optimize for timber yield. Well, after running all of these experiments, they wound up with a really high yield for a specific kind of tree that they really liked, which is called the Norwegian hardwood. And so Saxony and Prussia said, this is amazing. We've figured out exactly how to control nature, this really complicated distributed system, so that we could get the optimal yield from our forests. This is going to be awesome. All you have to do is figure out how to replicate this like everywhere. It turns out, though, that when you have a monoculture of exactly the same tree running amok in your forest, you basically don't have any ecology except for that tree. So all the animals that lived in the other trees, they're gone. They weren't there anymore. Their life cycles were not nourishing the trees that weren't the Norwegian hardwoods. The underbrush had been cleared out so that the foresters could walk along the tree line and see the height and the health of each tree. So we had made it really convenient for humans to understand this system, but in so doing, we basically destroyed the very thing that we were trying to optimize for. And the Germans called this, I'm going to butcher this German word, but it's called Waldsterben, or forest death. And basically, they didn't understand the underlying hidden variables that controlled the overall ecology. They thought they were optimizing for one thing by measuring the same variables across the entire forest, but they didn't really do that. They just didn't see the complete picture, and they weren't aware of what was actually happening in this system. And this is not a pattern that has been recently introduced. We have been failing at this for a very long time. The obsession of organizations trying to measure everything goes a long way back, even when it was really expensive to measure things. You know, now we can store stuff in S3 super cheaply, but conducting a census, for example, is astronomically expensive for a state. But a lot of states were obsessed with trying to do this. So one of my favorite examples of this is the Book of Lord Shang, which is a sort of an advice guide for Chinese rulers in the circa 200 BC era. And Lord Shang basically says, not in so many words, but if you don't build an enterprise dashboard that reflects everything about your populace, you will be deposed as a ruler. You will be overthrown because you don't understand how your state is doing. And specifically what he says in this book, this is, of course, a transliteration from the original Mandarin, but he says, if he who wishes to make his country strong does not know these 13 figures, these 13 magic variables, your state will become weaker and weaker until it is dismembered. And these were the 13 magic variables that he said were super important for everyone to know. The number of granaries you had, the number of officials you had, the number of useful people, the number of old people, weak people, the number of oxen, number of bales of straw, et cetera, et cetera. So you can almost imagine, like, if Lord Sheng had access to 21st century tools, that he'd be like firing up Tableau and throwing a bunch of metrics in there to be like, what does my population break down to? Oh, I have 41% able-bodied people and 18% weak people. I've got to like optimize for this, right? And a slightly more recent example, this guy is Sebastian de Vouban. He is, his title is Marquis of France, and he was really responsible, he was a military official, but he was really responsible for designing French fortifications. But that wasn't the thing he was most famous for. What he was most famous for was doing France's first semi-official census. And he kind of advised Louis XIV about how to consolidate the various localities that were just all these random French towns that were hard to understand about what was happening. And if you have 500 towns, they all speak somewhat different dialects. They all interact differently with the state. So it's hard to understand how those towns and cities are doing. So he said, wouldn't it be great, Louis XIV, wouldn't it be great if you could understand everything about your populace by just spending an hour and looking at some numbers that I'll show you, and then you'll be able to tell everything about your populace. Right? I'm going to give you this like perfect enterprise dashboard, effectively, that represents the health of your country. Wouldn't it be great if you just pay me like 100,000 francs worth of gold, and I'll go conduct this census, and in the meantime, I'll set myself up in this estate and just kind of administer things from there. But then, in exchange for that, you'll get this really clear picture of how your country is doing. So that's a really attractive idea if you have no idea how your country or state is doing because you don't collect these metrics. And there's this underlying presumption that like more data is good, right? So when you look at the terms of service for Facebook, Google, and Amazon, there's these really benevolent words like, we're going to personalize your content and help you connect to things or people, or maintain and improve the services in exchange for all the personal data you're giving us. And if you decide not to participate in the system, well, unfortunately, you may not be able to take advantage of many of the services that we have. So there's this really presumption of goodness of data, and if you don't participate in this idea, then you're going to be excluded from the benefits that accrue thereof. So again, there's a presumption that it's at least good, if not good, then at least it's not bad to have more data. And I want to challenge this by sort of examining what it means for us to process data as humans. So the other piece of this puzzle is that we have to eventually present whatever data we gather to a human who will be accountable for understanding and maintaining the health of the system. But humans have a lot of visual quirks. I'm going to invite everyone in the audience just to sort of breach conference etiquette for a second and put your hands behind your head and lock them together. And everything your fingers are touching right now is approximately where your visual cortex is. That's the part of your brain that lets you see me. That's the part of your brain that interprets pictures and images. You can put your hands down now. That's the part that lets you interpret images and understand shapes and colors and so on. And to show you that our visual cortex has particular kinds of things it's good at and not good at, we're going to do a brief exercise that you can all join me in. So on the following few screens, I'll be showing you a certain number of dots, and I'm going to ask you how many dots you saw on the screen. So there'll be a brief flash. It'll only be up for a moment or two. So how many dots do you see now? So raise your hand if you thought there was 1 dot, 2 dots, 3 dots, or 4 dots. Right, so there are 3 dots. It's pretty easy to count those. All right, now raise your hand, or now I'm going to show another picture of dots, and I'd like you to answer the same question. So raise your hand if you thought there were 4 dots, 5 dots, 6 dots, or 7 dots. So significantly more distributed this time. There were 5 dots. One more time. So raise your hand if you thought there were 6 dots, 7, 8, and 9. So even more distributed. So there were 8 dots there. And the reason that there's more of a distribution, the higher a number of dots is because humans are good at counting small numbers of things without having to count the individual items, and that's called sabotaging. So once we get under about 7 items, we can recognize what's happening at a glance without having to count or enumerate each thing. So when we have to assign a label like 1, 2, 3, 4, 5, 6, 7, 8 to individual items, that's called enumeration. But when we can see at a glance how many items we have, that's called sabotaging. Another quirk of our visual cortex is that when you see optical illusions like this, where the A and B squares are actually the same color, that feels very surprising, even though it's 100% true. Here's a bar of the same color connecting A and B to prove to you that it is, in fact, the same color. Or maybe you've seen this illusion where there are 12 dots on this. You may be able to see one or two dots at a time at the intersection of several of the lines, but it's really hard to see all 12 at the same time. If I reduce the contrast at the background, now it's probably way easier to see the 12 dots all at the same time. So it's because only the part of your vision that you're actually looking directly at has high resolution, and the rest that's kind of outside of whatever you're directly looking at will have much lower resolution. So those dots blend in with the background lines, and it's hard to see them when you're not looking directly at them. Another property of our visual cortex is something called apophenia. So we can often see meaning or patterns where there are no patterns. So this may look like a face, but it is not a face. If you went to a doctor and your face looked like that, they would probably say that you have some kind of medical condition, right? So it's not a face, that's just 3 circles and 1 horizontal line. Similarly, these are not faces. These are just stickers that you can buy on Amazon to put onto outlets. But again, not a face, but it looks like one. It's easy to see at least how this could be interpreted as a face. So there's sort of this fundamental mismatch between this idea we're really good at generating metrics, but we're not good at analyzing them, at least not at the rate that we're generating them. And I like to say that we're good at big data, but we're bad at fast data. So we're bad at paying attention to and understanding large collections of metrics. So in a world where we have things like memory, CPU, disk, 1,000 different metrics that we could measure, all of those metrics are competing for a much scarcer resource, which is the attention that we can pay to those metrics. And it turns out that measuring those things is super cheap. It's super cheap to measure memory or CPU or disk in a distributed system. It's super expensive to get a human to pay attention to what's happening with that system and understand 100 metrics. And this is sort of best summarized by a political scientist named Herbert Simon, who wrote a book called Designing Organizations for an Information-Rich World. And he said that when you have a lot of information, remember this is 1971, this is like way before enterprise dashboards or widespread computers were a thing. He said the wealth of information means a dearth, an absence of whatever that information consumes. So the price you pay for lots of information is a reduction in some other resource that you consume to process that information. And what he said is, what information consumes, in order to understand things, you have to pay attention to those things. And you don't have a lot of attention to use. If our visual system is fooled by 12 dots and a bunch of things like that, then we definitely are going to have problems trying to understand a distributed system where we're collecting hundreds of thousands of metrics. So my proposal is that we optimize for attention, that we not optimize for things like memory or CPU or disk or those sorts of things. We optimize for the human operator who is ultimately accountable for running that system. So let's talk about a real system and how we might measure it. So real distributed systems are messy. There are all kinds of, here's a topology of some arbitrary distributed system. It doesn't matter if these are applications or servers or VMs or Kubernetes pods or whatever. This is like a typical topology. It's just random stuff, different collections of it, all needing to be managed. Now, when you look at an enterprise dashboard of that stuff, though, it's not going to look like that. It's going to look like this really orderly representation of these neat rows and neat boxes of a grid-like structure that represents how this system is supposed to be doing. But that's just really sort of an aesthetically pleasing facade. It's just like the census from Vouban or Sheng Yang's metrics all over again. It reduces the complexity of what we have to understand, but it does so at the cost of throwing away the essential relationships that are necessary to understand what's actually happening with the system. And then we're basically back to the German forest scenario, where we threw away or didn't understand or weren't exposed to the real things that were important in this system. And a key observation here is that chunks of that distributed system are really different from each other. The topology that we saw before, these two groups look nothing like each other. So why would we try to measure components or parts of a system that are completely different and have completely different responsibilities in the same way? Why would we try to measure a distributed system by looking at the 200 VMs that it's on and then saying, you know what, it doesn't matter what those VMs or those components are responsible for. We're just going to measure the CPU, memory, disk I/O, and bandwidth, et cetera, of all of those components. And then that'll tell us something useful about the health of the system. I submit to you that it will not tell you anything useful about the health of the system and may even mislead you about the health of the system, so that you're getting, again, back into the German forest situation. So distributed systems are really different from each other in terms of, and even the components within a distributed system are often very different from each other in terms of the scale, the scope, the size, and the goals and responsibilities they want to have. So again, why would you measure systems that way? Why would you try to pick uniform metrics that apply to the whole system when it's really unlikely that that's going to capture a complete picture? And yet that's what people do all the time. That's what I saw all the time and continue to see all the time in large institutions like the kind I work with. So the first specific of my proposal is that we sort of embrace this inherent complexity. We don't run away from the fact that the components are all different from each other. We embrace the fact that the components are all different from each other, and we pick a metric that indicates this. So here's what I mean by that. Let's say that we have a system and we don't know anything about what's inside. We can ask this system any questions we want. What should we measure about how well the system is performing? And it doesn't matter whether this system contains, one thing or it's a complex distributed system under the hood. It doesn't matter. What questions, if we could ask the system any questions we wanted, if we could measure anything we wanted, what should we measure? What would tell us the most about what's healthy and whether it will continue to be healthy? So I think the key to that is a different sort of metric, a metric that is more closely tied to the way that the system is operating. And so the proposal is, instead of thinking about systems in terms of these really granular metrics like CPU, disk I/O, memory, et cetera, that we think about roughly four key properties of this system. The first property is what I'm calling demand, or how much work is the system being asked to do? If this is a database, you might say that work means something like the number of queries that it receives. But that might be a different thing for different kinds of databases. It would really depend, again, on the specifics of what the responsibility of that system was. But that's the first key thing here, is how much work is the system being asked to do? If the system is being asked to do a lot of work, we should expect to see a proportional increase in the amount of work it is doing if it's healthy. And we'll talk about that in a second. The second thing that I think is important in this overall picture is the output of the system. So of the demand that's coming in, how much is being satisfied? So if you don't have a lot of demand coming in and you see a decrease in output, that's not anything to get upset or alert about. That's fine. If you have a drop in demand, you should probably have a corresponding drop in output. So you shouldn't get upset or send alerts or send PagerDuty notifications or whatever if simply the amount of output drops. That's not the whole picture. It's a combination of how much demand is coming in versus how much demand is being met. The third attribute is efficiency. So how well does the system use its resources to produce the output? So if the demand stays the same and the output stays the same, but there's a decrease in efficiency, that's probably something we should be concerned about. Why did the system suddenly consume twice as many resources to do the same level of output? But if the efficiency doesn't increase or decrease, that's not something to be upset about if we see a spike in output. For example, let's say that the number of requests to your concert ticket website goes up by a factor of 2. you'd probably expect the amount of resources that this website consumes to go up by a sort of linear or proportional amount. Well, therefore, you shouldn't be upset if you see a memory spike or a spike in disk usage or a spike in the number of log requests that occur if the demand on the system is higher. So you would never set an alert under this philosophy for something like memory if you never set an alert just for that reason. You would want to look at how much demand is being met and what are you consuming to meet that demand. So in that example, the efficiency of the system did not change, even though the resource usage of the system did go up by a lot. So if that's true, then there's nothing to be alarmed about if you use twice as much memory, if in fact that's meeting all your demand. You know, that's what the memory is for. Why did you pay for hundreds of gigabytes of memory if it's not going to be used to satisfy demand? That's the whole point of it being there. So the capacity of the system is the fourth aspect here. Does the system have enough resources to do the work that is being demanded of it? So with those four aspects, we have a story that we can put together about the health of a system or a part of a system at any level. So you can imagine that a distributed system could be composed of many such subsystems, each of which has its own story like this. Now, the great disadvantage to the approach that I'm proposing is that it requires you to understand the system, or it requires someone to understand the system. That means someone somewhere must know what the responsibility of each of the components of a distributed system are. Maybe it's not the same person for all. It's not like one person needs to know everything. But there must be someone somewhere who understands that and can tell you what these metrics are, or can come up with a proxy or a reasonable approximation to the metrics there. So the cost and the trade-off here is that you have to understand the system that you'd like to measure. So you can't get away with just CPU, memory, disk I/O. Those metrics allow you to not have to understand anything about the system. The price of that approach is that you probably, because you don't understand anything about the underlying health of the system, the best you can do are just some rough guesses about whether it's really alive or functioning or not. So that is the big disadvantage of this, is that each one of those components is different. Each one of those components must have its own understanding of what it means for it to be healthy, and that understanding must be tied to, in some way, the work that it is expected to do or is responsible for. And then, importantly, we have to have those metrics be exposed so that they're observable. It's not enough to just measure this internally and then report something out. They have to be surfaced to whatever is doing your monitoring or whatever is understanding the health of the system. So let's look at some concrete examples. This is from a real situation. So we have a 1,200 pod Kubernetes cluster. They chose the metric of the number of queries that was received by this database that was servicing these 1,200 pods, or cluster of databases that was serving these 1,200 pods. And then they said the demand is the number of queries we receive, and the output is the number of queries that we processed within an SLA within the same time frame. So every second we're going to measure queries coming in, and we're going to measure how many of those queries did we process within our SLA. So if we see an increase in the number of queries received, we would certainly expect to see an increase in the number of queries we process within our SLA. If we don't, if we see demand go up, but output doesn't go up, that's a problem. That means we're dropping a bunch of queries on the floor. There's a difference between the demand that we have and the output that we have. So second example, concert ticketing website that at its sort of peak load gets 10,000 requests per minute. So we get a request for ticket reservations to see Britney Spears or whatever. And then their metric for output is how many of the tickets that we got requests for were sold with no negative UX experience, or without a negative UX experience. So did we drop their credit card processing? Did we time out on some web request? So the extent to which we avoid doing that, we're going to count that as successful. And then finally, this is from a 1,000 patient hospital's electronic medical record system. This is where your patient records go. And they measured the health of the system by looking at how many requests for patient records did we get from either doctors or other automated systems at the hospital, and how many of these did we return within a reasonable SLA. So similar to the concert ticket example, but for something that's a lot beefier than a single web request. A patient record could be dozens of megabytes, lots of PDFs, lots of data from external systems all being bundled together. So with this approach, with this embracing of the inherent complexity that's in these systems, by understanding what those systems are doing, like each of these three examples, we had to know what that system was doing. We couldn't just say CPU or disk or memory. We had to understand that this was a database and its job was to process queries, that this concert ticketing website's job is to sell tickets, and that this hospital's patient record system is to serve you patient records. These are not opaque VMs that you just get to monitor for free with like CPU, memory, and disk, and so on. And again, I want to emphasize, it's not that CPU, memory, disk, et cetera, not that these low-level metrics are not good to measure. You should still measure them. It's that they're not sufficient for understanding whether the system is doing its job. If I just tell you that a system is at 80% CPU, does that tell you anything about whether the system is alive or healthy? Probably not. Probably just tells you that it's at 80% CPU. Does that mean it's at 80% CPU because there's a pegged batch job that's been there for 24 hours doing absolutely nothing? Or does it mean that we actually have a lot of demand from Black Friday on our site, so we're approaching the limits of what the system is capable of? So that's the embracing of the inherent complexity, the complexity that was worth it, that represents the responsibility that the system is doing. Unfortunately, there's also a lot of accidental complexity. Not all complexity is good. So complexity that arises from, in your monitoring, from arbitrary decisions on your part that have nothing to do with the underlying system, that's the bad kind of complexity. That's the complexity we'd like to avoid. There's a lot I could say about how complex different monitoring systems are and how some of that is wrong, but I want to focus on one specific kind of accidental complexity because I see it literally everywhere, and that is setting arbitrary thresholds like alert me on 90% of CPU or alert me when my free memory drops below 5% on some system. And this threshold alerting also applies to cases where you're monitoring metrics that look like that too. It would also be wrong to set a threshold alert on the number of patient requests you get or the number of patient records returned. Now, the reason that that's wrong, and that may be a little shocking because every monitoring system that I can think of, it certainly at least encourages reporting or recording alerts based on threshold monitoring. And in some cases, that's the only way to do alerts. You only get the choice of tell me when it's within this range or above some threshold. So here's a graph of CPU. It doesn't matter really what it is. It just matters that you can see the shape. And the spike that's right here corresponds to a bad event. We didn't want the CPU to get this high. This caused a problem with our patient record request getting served. And the same is true of this spike and that spike. But these spikes are fine down here. Although they are spikes, they did not affect our ability to process patient record requests and reflected just increased demand without a corresponding decrease in efficiency. So so some of these spikes are bad, and some of these spikes are good. So if we were going to set an arbitrary threshold, like tell me when I hit the 95th percentile of CPU in the last, say, 30 minutes or whatever, that would enable us to be alerted on one of those cases, but we'd miss a few of the others. And so we could say, okay, well, I missed too many. That was a lot of false negatives. I did want to be alerted about those things. Those should have actually been positives. So I'm going to move this bar down and say, okay, next time that happens, please alert me on those two. Well, you're still missing that one, so you say, okay, I missed that one too. Next time it happens, I want you to tell me about that too. So the only way that you know that that's a place to set it is because you had to wait for 4 failures to happen before you saw a problem, before you saw some way to respond. So, and the position of that line is also arbitrary. Like, why is it there? Why isn't it lower or higher? Why isn't it right below the 4th dot? Why is it should there be some margin between the lowest failure you've seen and where you want to be alerted next? And so one alternative to setting threshold metrics is to use what are called quantiles. So here's a arbitrary system. Here's some resource measurement of this system. And the consumption of this resource fluctuates over time with a couple of outliers. You can see here we've got some really big spikes in the consumption of this resource and some really big dips in the consumption of this resource. So a better way to maybe understand this system would be, what if we sorted all of the samples that we received and then looked at how the distribution of those samples appears? So if we do that sorting, we wind up with something that looks like this. As you can see that there's a few outliers towards the end and a few outliers towards the other end. But overall, we can see that the shape of this data tells us that we pay a relatively linear cost for consuming this resource in the presence of some kind of demand. Except near the very end, then we have very different kinds of behavior. There's something different about the endpoints of this graph. And I will posit that a better way than threshold metrics is to understand the shape of, is to take this approach. Look at the shape of the graph, and where the shape differs, there are mathematical techniques that can tell you this, where the shape differs. So if we zoom in on this point, where we might want to explore is the point where the graph starts to diverge, where there's a change in the behavior, where it seems like the previous model that we were working from is no longer correct. That's the part that we would actually want to alert on when we reach that stage. Not when we reach an arbitrary threshold, but when the shape of the data is actually different. That's what we should actually be alerting on. So when that linear relationship is no longer true for some amount of time, that is the metric we'd want to look at. Now, that's still arbitrary, right? But it's less arbitrary than saying 90% CPU. Because 90% CPU is a guess. It's basically just saying, I think that this system above 90% CPU enters some new and dangerous mode that I would like to be alerted about. That is a complete fabrication for almost all systems. Unless you know something about the intrinsic way that that system operates, it is a complete guess to say that 90% CPU or 85% memory or whatever is the thing that you want to be alerted on. But this is less of a guess. It's still a guess, because it might be true that, in fact, this corresponds to normal behavior, but it's less of a guess. And it's certainly more true that this linear relationship looks very different than this relationship, which looks to be sort of pseudo-exponential right here, like linear right here at a different rate, and then maybe starts to be exponential. But it's less of a guess to do that than to say that we want to use threshold alerting. So that's the big thing, that if you could correct one thing about your monitoring system, I would avoid threshold-based measurements, or alerting rather, and instead focus on these shape-based measurements, using these quantiles to understand the overall shape of the data, and then alert when you're outside of the what would be considered the normal behavior range for that. So if we can use that story to understand the raw data, if we can use these metrics like queries received versus queries processed to understand what's actually happening at an underlying level, we can reduce the number of false positives we have. For example, if we're not using threshold-based alerting, and we're just sort of looking at the story that the system is telling us because we're measuring the amount of work that's getting done versus the amount that's being demanded, we can get a really different understanding of the health of our system. So that database example from before, let's say that the number of queries that we receive goes up by 20%. Now, if we didn't know anything about the rest of the system, what would be normal behavior is for the queries processed, the output, to go up by 20%. And we would expect the resource usage to go up by 20% if the efficiency stays the same. So that would be normal. What wouldn't be normal is if the usage went way up, meaning that our efficiency went down. That's something to alert about. So even if we're meeting the demand, if we're suddenly using way more resources to meet that demand than we were before, that's a really big hint that we've entered that part of the curve that is anomalous for our particular part of this distributed system. Now, conversely, if the number of queries went up and the usage went up by about the same amount, but the number of queries processed, the output did not go up by a similar amount, that's also something to alert on, because that means, again, we've entered that part of the distribution of the quantiles that tells us that we're not getting the same output that we were before. So again, these other metrics are important too. CPU, memory, disk, these are important for understanding when there is a problem, like the kinds we just saw before. When there is a problem here, we do want to be able to diagnose that problem. What were the underlying metrics at the VM level or at the infrastructure level that caused that? Is it maybe that the CPU got pegged, so there was no way to, maybe we were spending all of our time swapping to disk when memory was maxed out, and that's what caused the latency, which then caused the drop in output? Then it's great to have those metrics at your disposal. But merely having memory high, or merely having CPU high, or merely having disk I/O high, et cetera, does not tell you about the health of the system. It's this picture that tells you about the health of the system. It's that picture, sorry, that tells you about the health of the system, not the CPU memory disk picture. So again, still important to monitor those things, but if you're going to monitor something and you're going to show somebody something, you want to optimize for their attention so that you don't show them 100 things. You show them the story about that particular part of the system or the overall system and how much work it's doing. That is what I mean by optimizing for attention. Optimize for something the user can understand, the operator can understand, and which tells them actually whether the system is meeting its responsibilities or not. CPU, disk I/O, memory, et cetera, those do not tell you anything about whether the responsibilities of the system are being met. So earlier I said this requires a lot of work. You do have to understand the system in a way that wasn't true before. Is it worth doing this? So I'll present some anecdotal evidence. I'm allowed to present anecdotal evidence because I don't have any research funding, so you'll have to take this for what it's worth. So I tried this experiment out with 3 Fortune 100 firms. There was a mean 98% reduction across the systems that we tried this for in the false positive rates. So number of pager duty alerts, in other words, was reduced by a factor of 50. Went from about 500 alerts per week for this one system to 98% lower than that, right? So that's a really big reduction. Imagine now understanding that when you get a pager duty alert, it is actually important instead of like, oh yeah, this thing rang my phone for the 500th time today. The second data point is that there was about a 1,500% improvement in correlated outcomes, meaning that not just was the false positive rate better, but also the correlation between what was being measured and the ability to predict when there was about to be a failure went way up, when it went up about 1,500%. So the p-value, R value, if you want to be statistically technical about it, that improved by about 1,500%. And maybe more tellingly, all 3 of the firms that I've tried this approach with have expanded it to new systems that they are managing or operating or building. They liked it so much on the experimental systems that they have expanded it to new ones. But even more tellingly, they're investing to backport it to the previous systems. They're investing the effort to expose these metrics so that they can be observed by whatever their monitoring system or monitoring tools are, so that those metrics can then be surfaced to operators. So if you're going to take away a few things from this talk, what should you take away? First, humans are more important than computers, so you should put humans first and favor the metrics that tell a story about the responsibility of the system being satisfied or not. To the degree that the responsibilities of a system are being satisfied, that's how happy you should be that the system is doing its job. There may be ancillary concerns, like perhaps you don't actually understand the responsibilities of a system, but that's a separate problem you'd have anyway, right? Someone somewhere needs to understand what the system is supposed to be doing and whether it's meeting its hidden or actual goals. The second takeaway is that your attention is the scarcest computational resource of all. If you have 100 developers or 100 DevOps people responsible for managing some system or some operational responsibility, and you show them a bunch of dashboards that just have CPU, memory, disk I/O, et cetera, what are the chances that you're putting them to the best possible use versus just having a bunch of eyeballs staring up at a TV that is an information radiator? That's not the best use of those people's attention. It would be better to optimize for their attention and have a dashboard that indicates the responsibilities of a system being fulfilled or not. And to that point, there's always more things you could be measuring. There's always more metrics you could be inventing, combinations of other metrics, relationships between the metrics, relationships between different systems. But there's never enough attention to process all those metrics. There's always a dearth of attention to process and understand the health of a system. So make it as easy as possible on yourself, on your operators, on the people who are responsible for maintaining the health of the system, and optimize for attention instead. So thank you very much. If you have questions and you didn't during the talk, pick up your phone and send me a tweet. Now is the time to do that. So I'm going to go through the people who've already tweeted me and respond to questions. All right, let's see. First question. Okay, several awesome jobs. Let's see. Okay, here we go. First question. I'll phrase, this is from Cesar. I'll phrase this as, if it's too hard for my system to expose these metrics, what's the right way for me to do that? So if you have a system that you are responsible for, but you can't change anything about the system, what should you be measuring if not CPU, memory, or disk I/O? So if nobody's investing the effort to expose the responsibility and work type metrics, how do you actually show those metrics? I think that's what Cesar was asking there. So great question, Cesar. Thank you. My advice is pick the closest proxy you can get to that work. If you don't actually have that, pick the closest thing you can get to it. So if you can't invent a new metric, or if you can't surface a metric that represents that, something that's a little bit farther away from CPU and disk I/O, et cetera, if it's closer to telling the story of the responsibility of a system, is probably better than nothing. So in the database example, if you have, if your database's clusters are sitting on a set of VMs, instead of measuring the CPU, memory, et cetera, of those VMs, what you could measure is the queries done by the database. You could write a small query to maybe hit the system table of that database and say, show me the number of queries you processed in X amount of time. That doesn't require changing anything about the underlying system, but does expose metrics that maybe weren't being exposed before. Okay, next question. Oh, no, that was the last question. Okay, cool. Only one question, awesome. If you have more questions, I would be delighted to answer them on Twitter. I think I'm slightly over time at this point, so I want to thank you all for your attention and for coming to my talk. And I hope you have a wonderful rest of the day here at Spring One Platform.